bit more to tell you about determinants. So, in particular, I want to share with you the classical formula for the inverse in terms of the adjoint. So this adjoint, well, let me not write. Let me project. If I start writing things before you know it, we'll use 30 minutes of class time, and we have more important things that I should write today. So this is really just a formula to know about. It's not a formula I recommend that you memorize. I once was teaching a student, and I told them in no uncertain terms, I said, this is something to know about. This is certainly not the way to calculate the inverse of 3x3 matrices. This is not what you should use to calculate the inverse. I'm looking at his test and what is this? And then I realized Min had memorized this formula. It's so annoying. Don't do that. Don't be Min. Okay, anyway. Did you get it right? There's a little danger Min that's watching this. What? Did you get it right? Yeah, I think so. He can remember some formulas. But that's really not the point of this. Anyway, so the matrix of cofactors is called the adjoint. And the ijth cofactor, Cij. Now, the ijth cofactor is actually defined by minus 1 to the 1 plus I plus j times the determinant of the submatrix. So, what is Cij? Cij, the ijth cofactor, Cij, it's equal to minus 1 to the I plus j times the determinant of, the, let's say, matrix with, the I and jth row and column deleted. And I forget which one it is. But anyway, that's in the notes, the specific which one's I and which one's j. But, well, for example, for the 2x2 case, the cofactors, so for A, if you cross out this column and that row, you're left with D. Minus 1 to the 1 plus 1 is just 1. B, if you cross out this, and that, you're left with C. There's a minus because it's minus 1 to the 1 plus 2, which is 3. Minus 1 to 3 rows. So this is the adjoint. Now, you remember the formula we got in the inverse was kind of like this, but the B and the C were switched, right? So if you look at it, this was the formula we got for the inverse. D minus B minus CA, that's our go-to formula for 2x2 inverses. That's good for not just this class, it's good for about, 3 or 4 other classes at this level, right? That's something you really want to just have hardwired. That formula I do think you should memorize. But if you look at it, what it really is just 1 over the determinant times the transpose of the adjoint. And that,
only 2x2 case, right?
no, that is actually in general. So that's a formula.
Oh.
I mean, in the 2x2 case, that's the formula. Let me show you. In the 3x3 case, here's the here's the 3x3 case. If you calculate the cofactors, here they are, 1, 1, 1, 2, so on and so forth. So for example, 3, 3, I cross out the third row and the third column, and it leaves me with A, B, D, E, which is in the upper block. And so the cofactor, the adjoint, right? It's a matrix where each entry is formed by the determinant of the submatrix formed by deleting the ith row and the jth column with its sign factor, the plus minus thing we saw in the Laplace expansion. So anyway, the adjoint transpose is this. And so if you really wanted, and you don't, to memorize the formula for the inverse of a 3x3, there it is. There's a good reason this isn't in books. It's because professors smarter than me realize that if you put this formula in a book, students will use it. So don't use this. What am I showing you? I don't know. Don't use it. Seriously. Don't use it though. Yeah.
Oh, they're not.
No.
Why would we use this when we already know that
Yeah,
we
yeah.
already have the matrix with
No, right. Exactly. The method we taught you before to calculate inverses is far superior to this. Yes, Dr. Professor Landon.
If we do use it, is it wrong?
yes, it is wrong for you to use it. I mean, in the
If we have extra time on the test and we wanted to show
metaphorical
off,
sense.
we just save the inverse problem for last. We just calculate the inverse that formula.
The fact of the matter is, much like the students who use the quadratic formula with a given factor, do it at your own risk, right? By and large, people, when you can factor, it goes better, right? Try to use quadratic formula, square things, squared, subtracted. By and large, students are going to make a mistake there because it's a formula. You have no sense of, where it's coming from. And the same goes for this inverse formula. Yeah, it's nice and all, but it's not a good idea to use it, really. The proof, I would recommend read proof 2. Proof 1, I'm not so sure about. Proof 2 is actually pretty easy to follow. There's a typo in here, I noticed. Somewhere I had written A inverse is determinant of A times adjoint transpose. That's wrong, obviously, but I don't see it now. Anyway, the proof is just by Cramer's rule. With that, I'm going to put this away. So. All right. I will give you a token application of determinant before I get into the eigenvector stuff. This application is pretty typical. So determinants are great for writing formulas of a lot of different things. So here's an example. And I think if you understand this example, you might realize how to use the determinant to do other things. So here it is. If you look at the determinant of, let's say, how's it go? Forget what I put first. Oh, where did you go? There it is. So 1, x1, y1, 1, x2, y2, 1, x, and y. Now, if I set this equal to 0, what is this equation? So think of x, x1, y1, and x2 and y2 as being given. And on the other hand, x and y are variables, okay? Think of it that way. So if you like, I could put in, to make it less. Here, let me tell you what, let me make it like a little bit less esoteric. For example, we could look at determinant of 1, 2, 3, 1, 4, 5, 1x, y. What would this be?
X, y, 0, right?
Well, that's the thing about determinants. When is the determinant 0?
When the columns are linearly dependent.
When the columns are linearly dependent, or to this example, it's more interesting to think about rows. When the rows are linearly dependent, right? So if you have a repeated row in particular, it's 0. So if you look at this formula, this thing is automatically 0 when 0, in 2 cases, right? There's 2 obvious cases. How about x equals to 4, y equals to 5? And it's also 0 when if x is equal to 2 and y is equal to 3, right? And if you think about the formula for a determinant, what's it look like? It's basically linear in the entries, right? So the fact that there's only one x and one y means that you have at most like the first power of x and the first power of y appearing in the formula. So what you're looking at is a linear equation in x and y, right? A linear equation in x and y, which is 0 when you plug in what? The 0.45 or the 0.23. So this is the equation for a what? It's a line. It's the equation for the line. This is the 2-point formula for the line. When I took linear algebra, we had a Maple lab, and we actually put in symbolic matrix, and we had it simplified and out popped the 2-point formula for the line in the test. Maybe that would work here. Yeah.
Can you say again how that's aligned?
Huh?
How do you align to that? Or?
Well, it's a linear equation that when you plug in this, you get 0. When you plug in that, you get 0. So what is that? I mean, if you have a formula of the form ax plus dy equals to c, right? That's a line.
Yeah.
That's what this is.
Okay.
But then b equal to, or a, b, and c equal
Those are just coefficients. I mean, you want me to calculate it? I can.
I mean, that's what I was curious about, was like, what
I mean,
process.
we can work it out, it's no big deal. 1 times 4y minus
just because it
5x
has-
minus 2 times y
Because
minus.
it's two variables, right? That's basically
Right.
the idea.
Yeah, well, I mean, part of the point here is I don't have to do this because I know properties of determinant and I realize that this is first order in x and y. So that means it's of that form. And then you can simplify this, but eventually you'll get to something like this.
Basically, if you added a z in there, if you replace one number with a z, then it would be a plane. with
Right,
like
so
that.
you can see how to write the 3-point formula.
If there was like an x squared, it would be a parallel.
Yeah, so for a plane, you could write this, right? 1 x naught, y naught, 1, oh, let's see, I guess I need a 4 by 4, huh? Z naught, x1, y1, z1, x2, y2, z2, x, y, z.
Okay.
So if you
Yeah,
look at
makes
that,
sense.
yeah, that'll give you the equation for, assuming that it's automatically 0 because I have to assume that those points are not collinear. No, excuse me, the points are not collinear or the same point.
Okay.
I guess that would still fall under collinear, but yeah, and of course, yeah, once you do that, then you can see how to do it for higher planes, let's say. And you can also use this trick to write down differential equations that you like. Like suppose you want a differential equation that has solution, suppose you want the solution y1 equals e to the x, and you want the other solution to be y2 equals sine of x, Suppose I want that differential equation. Well, I could do this, I think. Well, anyway, I had that in the notes. Let me go on. Now I'm digressing. There's a few more examples. I mean, my point is,
It was interesting though.
you can play with this trick more. There's more. I think these are called van der Waals. Well, the van der Waals is like this. I'm not sure these are. Let me stop with the name calling. Let's go on. So, listen, guys. There's many more things to say about determinants, and we will see some of those as we go on. One of the major applications of the determinant is to the problem of eigenvectors. So that's where we are. And I'm trying, basically, guys, to cover, I'm in this book, right? And so we're at chapter 4 now. And I think it's good. I tried to read it last night just to try to get it in my thinking. I won't say everything he says in here, and I think if you read what he has to say, you'll profit from it, okay? But my goal this week is to cover sections 4.1 through 4.4, roughly speaking. So let's get to it. So, excuse me. Eigenvectors and eigenvalues. Let's talk about it. It doesn't really matter if you can spell it or not. I will soon replace this with e vector and e value. And as he says at the start of all this, it's kind of a hybrid word, right? Like eigen is from German, but obviously vector is English, right? Perhaps a more consistent nomenclature would be characteristic vector. Characteristic value. So these things, they help you understand. So what we were studying, let me just set the stage here. We want to study a linear transformation. So what are we studying? We're studying, so we're given, a finite dimensional vector space V, say, an n-dimensional vector space over the reals. All right, and what we really want to study is linear transformation T, which goes from B to B. All right. So we already kind of know what the structure of the vector space is by itself, right? We don't even find a basis for it. It's got n things in it. There's an isomorphism to Rn. That's kind of all she wrote, right? So studying eigenvectors and eigenvalues is really all about T. It's about understanding the structure of this linear transformation, trying to understand geometrically what's it look like. as best as we can. It turns out this concept of an eigenvector is very illuminating. So let me just define it for you. So here's a definition. We say x not equal to 0 is an eigenvector with eigenvalue, say lambda, and lambda has to be a real. And so I will also allow the terminology complex eigenvalue, but let's just agree for now we'd say that if lambda, if what we're thinking of as being lambda, if that ends up being complex, for the moment being, we're just going to say it's not an eigenvalue, okay? When I say eigenvalue, understand that by default I'm talking real eigenvalue, okay? At least for the moment. So with eigenvalue lambda in the reals, if the following, if t of x is equal to lambda times x, that's it. Okay. Now in the book, indeed he has some infinite dimensional examples, and that's fine. I mean, I can give you one too. What's an example of an infinite dimensional space with an eigenvector? So just to give you a kind of weird example to start with, how about this? Look at V being the space of functions. They smooth functions on the reals, right? You could think about the derivative operator. You think about t equals to d dx. So if you're looking at the eigenequation, you're looking at something like, let's say t times the function f is equal to df dx, right? And that would be equal to say lambda times f. Now maybe if I traded f for y, you'd be able to solve that calculus too, right? You make it more familiar that y equals to f. We face dy dx equals to lambda y, right? So you can separate variables. You got dy over y is equal to lambda dx. You integrate both sides. You get natural log f value y is equal to lambda x plus some constant. And then before you know it, you've got y is equal to some constant, say c1 times e to the lambda x. So, so this is a so-called eigenfunction of the derivative. So this concept of eigenvector, it has application certainly beyond the narrow confines of n-dimensional vector spaces. But I really don't have much to say about the infinite dimensional case except to share with you this example and to tell you that in fact you'll find eigenvectors, eigenvalues, indeed generalized eigenvectors and eigenvalues. We won't learn about those for a while. They're all in, differential equation is full of these things if you start looking for them, okay? So what I'm about to share with you in the finite dimensional case has application beyond our narrow n by n matrix confines. Now, you may or may not be you may be more or less rusty on this calc too. That's kind of just, I just included some details here for the sake of trying to remind you, but it's not really what we're doing here. Okay, so let me erase the evidence and go on. Okay, so what's a better example? How about this? If I have a diagonal matrix, right? Say D1, D2, Dn, and I define, let that be the standard matrix of T, right? So I have, if you look at it, what would like T of D1 be? You get back, you get D1. In other words, you get what? You get D1, E1, right? So for a diagonal matrix, if you look at the linear transformation, which is induced from a diagonal matrix, what are eigenvectors in this case? Just E1 is one, right? What's the eigenvalue of E1? you read it? What's lambda 1 equal to?
D1.
D1, right? Yeah. So likewise, T of EJ is equal to DJ EJ because it's a diagonal matrix in this case, and so therefore, EJ is eigenvector with an eigenvalue lambda j equals to the diagonal value. Yes.
So, is this related? Okay, so like the D1 would be called the eigenvector, right?
D1 is the eigenvalue. D1 is a number.
Okay. Well, like the coordinate math we did when we studied isomorphisms and stuff. Like, would those be?
We haven't talked about eigenvectors yet, though. So
But I mean, would they be eigen? Like, you know how we got the coordinates?
I have not discussed eigenvalues or eigenvectors up to this point yet. You might find some somewhere, and there will be connections with things we've done before, but not yet. So this is a very simple case. And in some sense, this is like, in some sense, putting the cart before the horse. Actually, our whole goal, really, is to take other matrices, right, and make them look like this one, as it happens. So certainly a diagonal matrix has easy to find eigenvectors. They're just, the standard basis is eigenvectors, all right? So let me share with you a little bit of theory then before I give any more examples, because we really need some theory here. So, theorem. Lambda is eigenvalue for t v to v if and only if the kernel of t minus lambda I is not equal to 0. Okay. Moreover, in this case, lambda must solve the characteristic equation. The characteristic equation is the determinant of t, let's say minus xi, is equal to 0. So in other words, if I put x equal to lambda, we get a solution. Okay? This is really the central theorem of all of chapter 4. This is where everything happens, okay? So it's important we understand this. And it's really easy to understand the determinants. Let me show you how. So what's the proof going to look like? So it's if and only if, right? So let me start with the forward implication, yeah? So what am I going to do? Assume lambda, yeah, assume lambda in the reals is an eigenvalue. Then what? There exists x not equal to 0 such that what? T of x equal to lambda x. That was our definition, right? So then what? I'm just going to pick on, by the way, the first sentence to start with. So let me just kind of fracture this theorem into pieces. We'll take care of the moreover part next, all right? So let's just take care of that to start with. So all I need to show is that the kernel of t minus lambda I is not equal to 0. How do I do that? Well, it's really not much to do here. So you just say, okay, well, that's t of x minus lambda x equals to 0, right? And here, to be clear, I said I here, but what I really should write is the identity, right? This I should really be, when I write I there, what I intend there is the identity function from v to v, right? Which is a very boring function. Id of x is equal to x for all x. It's wouldn't have a very large Twitter following or anything. It's really not that interesting. It says back to you whatever you say to it. Hey, this is psychologist. But anyway, so you have t minus lambda times the identity, all times x, all, not times x, but operating on x gives you 0. But what does that mean? That means that x is in the kernel of that operator. Right? And x is what? X is non-zero. By definition, eigenvectors are non-zero. If you get nothing else from today, remember, eigenvectors are non-zero. If when you're working out on the test, you find the eigenvector is 0, you know what that means? That means you did it wrong. That means that your eigenvalue isn't really an eigenvalue. Because if you calculate an eigenvalue wrong, you'll get, well, that'll be, stop talking about, just a minute, and then I'll make this comment more clear. So this is not equal to 0, right? Okay, that part of the proof's done, right? How about the other direction? So what I should do what? Assume, there's really, it's almost, I probably could do a bidirectional proof here without losing people. I'm doing both directions just to drive the point home. Assume that the kernel is non-zero, right? What's that mean? So therefore, there exists x in the kernel, right? Right? Such that what? X is not equal to 0. Then what? T minus lambda times the identity acting on x is equal to t of x minus lambda times the identity acting on x is equal to 0, which implies that t of x is equal to lambda x. Right? Hence, x is eigenvector with eigenvalue lambda. All right? So that takes care of the first sentence in the theorem. How about the second? How do we know that lambda must be a solution to the determinant of t minus xi? 0. So consider the operator, t minus lambda, t minus x times the identity, okay? Let me call this thing, let's just give it a name, so you're tired of writing this, let's call it S, okay? You can call it S sub x if you want to emphasize that it has an x dependence, right? Or S of x if you want, I don't know, whatever. If S sub x is invertible, right, then what? What does that mean? For one thing, it means it's injective, right? That means it has kernel 0. Right?
The determinant is also non-zero.
Exactly. And of course, the determinant of S of x would be not equal to 0. Exactly. So in fact, in that case, we know that this operator S, of x, does not have an eigenvector. Sorry to use x over here as the eigenvector and x over there as a variable. I don't intend them to be the same. Tell you what, to make this a little bit more clear, let me use a t here instead of an x. I don't want to tempt you to think that x is the same as the eigenvector. It's not. That's just a real variable, okay? T. Oh, but I use t. Fine s, little s. There we go. Oh, man, I just can't win for losing.
Just use a little t.
I use little s, but then I gotta use something else for this. I don't.
No, just use something Greek.
My s.
I wrote in pen.
You wrote in pen? All right.
Why didn't you just keep it X? There's like.
Fine, I'll keep it x.
I mean, use Chi.
I find myself agreeing with Christian. I know I did something wrong.
Have you read it?
All right.
Like 200 points you
Okay, so the determinant's not 0, right? In the case that the kernel is 0, right? But you see from this argument over here that if the kernel is 0, there are no eigenvectors, right? With eigenvalue x at least, right? So if I want x to be an eigenvalue, I need what? So we need, we need the determinant of s of x to be equal to 0 in order that what? The kernel of t minus x times identity not be equal to 0. In that case, there will be eigenvectors, right? Now, how do I know that it's, you could say, well, just because it's not invertible, that doesn't mean that there's automatically a solution, right? It could be an inconsistent system. But that's not the case here, right? Because you're looking at the kernel. There's always 0 in the kernel. So it is a consistent system. So what that means is, by the way, if there's one eigenvector, there have to be infinitely many of them. Right? Because that's your choice. If you have a linear system of equations, you either got a unique solution, no solutions, or infinitely many. When we're talking about eigenvectors, we're always talking about infinitely many solutions. All right? Until we make a little adjustment to our request and say, find a basis for the eigenspace. Then we're talking about a selection of a particular eigenvector from this infinite family. But I'm getting ahead of the story. Yes, Len?
Does that have any relation to the fact that like there's infinitely many bases?
I'm not sure I'd sign up for that. So that's the determinant of t minus x times the identity must be equal to 0 when x equals to lambda is an eigenvalue. All right. At this point, I'm going to transition. I could keep talking about the theory for eigenvalues and eigenvectors in terms of an arbitrary linear transformation acting on a vector space. Indeed, most of what I tell you holds for that. But when you really get into the calculations, what you're always looking at is a linear transformation for Rn to Rn. And as the authors of the book explain, and this is also explained in my notes, if you understand this problem for Rn, you can easily abstract to the case of linear transformation. So mostly we're interested in the case that we're looking at an n by n matrix, right? An n by n matrix will uniquely represent one of these linear transformations. So I'm going to shift gears and then try to look at that. Let's see here. So basically nothing really changing here. Nothing really much changing here. Because the determinant of a linear transformation, right? How do you define it? You define it by the determinant of the matrix which represents it with respect to some basis. Now, we're talking about t going from b to b, right? So the definition for determinant of a linear transformation is just pick a basis, and you calculate the determinant with respect to that basis. The reason this is a reasonable definition, what happens if you chose a different choice of basis? What would that look like? Similarity transformation, right? It would just be something like P inverse, T of beta bar, P, right? Which would, by the way, be, because of properties of determinant, right? We can split it into 3 determinants, the determinant of the inverse and the determinant of the P, they cancel. and you're just left with the determinant of beta bar. So essentially the point here is it suffices to just focus on this. So we'll focus on the structure of, say, A in Rn by n, okay? Because basically, T is going to have, we can easily prove that T has, it essentially says is if T of x is equal to lambda x for some x not equal to 0, that's true if and only if the matrix which represents T, right? Let's say T beta beta times, let's say V is equal to lambda V. And this is for some x in vector space V, whereas this is for some V in Rn. Okay, so and the coordinate mapping is getting us between these worlds. So it suffices that if I can just understand over here, I can easily go back over here when I need to later, okay? So let's focus. And nobody wants to write T beta beta everywhere, right? So instead of looking at this, we're going to trade this for the much nicer symbolic problem of A, right? So. All right, so just to read, and just to beat a dead horse, A in Rn by n has eigenvalue lambda in the reals, if and only if there exists x not equal to 0 such that ax equals to lambda x. All right, and then of course x is the eigenvector with eigenvalue lambda, right? All right. So, immediate observations then, right? Because of the theorem I just erased, what can we need? We need what? We need the determinant of A minus lambda I equals to 0. So we usually use lambda as the variable. If you don't like using lambda as a variable, if you want to reserve lambda to be the solution to the equation as opposed to the variable for the equation, put a t there or an x there or something, okay? But you understand lambda is being used in two senses here. It's being used as a variable. So anyway, if lambda is an eigenvalue, then we need to solve this so-called characteristic equation. And we can trade ax equals to lambda x for A minus lambda times the identity matrix times x is equal to 0. The reason we should do that is what? Why should we do that? Why should we look at A minus lambda x equal to 0 as opposed to ax equals to lambda x? Why is the latter vastly superior to the former?
You can row reduce it.
Right. In other words, we already own that problem. That's a null space calculation. We know where it lives. You can find it. Put it in jail or whatever. Confiscate its drugs. It's money in our coffers, whatever it is that you want to do out of it. Sorry, I think I may have been watching too many game-related cop shows lately.
That was like
You want
Canada,
baby
so-
carrot?
Don't want a baby carrot. I don't want that processed carrot food. The baby carrots aren't really baby carrots, it's a machine. Sorry, my mom.
I'm not like crazy, I'm not like hallucinating yet.
All right. What's right? I don't know. Just tell me the time it is. Like,
It's 12:15.
No, I'm kidding, 12:07.
12:05. It's 12:05.
Okay.
I'll watch 2 minutes ahead.
all right. Thank you.
Well, the first time I was, but
Okay.
I was going to tell you the truth.
So, how do you find eigenvalues and eigenvectors? All right. How do you calculate them? Those are sort of immediate tasks we'd like to understand. We'd also like to understand why I look at eigenvalues and eigenvectors. I've said almost nothing motivating today about them. I've just showed you what they are and how to work with them, right? I do think the textbook does a pretty good job to motivate them. I'd like you to read that to get some sense of the motivation. My notes also attempt. So my notes is like chapter 11. I'm not completely sold out to the textbook yet. I think you still have something to gain from reading my notes on this stuff. Just chapter 11. I haven't asked you to do that, except I'm kind of asking you now. Read the textbook first. I think it's better. But
Read both of them
that'd probably be wise. Maybe read the textbook to start with, do your homework, and then later, before the test, read my notes. Maybe it'll help it gel. There's a bunch of theorems about eigenvalues and eigenvector. Here's one. Here's one theorem. Lambda equals to 0 is an eigenvalue if and only if A is not invertible. There's a theorem. Oh. Oh. That's what the baby carrots were about.
You seriously didn't see them until what? Okay. No, it's very
I'm very unobservant. I mean, this should not come as any surprise. Anyway, so
I was starting to think I was crazy. I was
look at this. So
yes.
that's okay. So the forward direction, you notice that if lambda equals 0 is an eigenvalue, that means that there is an ax equals to 0 for x not equal to 0, right? So therefore, A inverse does not exist, right? Because one of our list of one of the things we had earlier for the matrix to be invertible or not was that if the homogeneous solution has a non-trivial solution, the matrix is not invertible. So game over. That's the and the reason is in reverse direction. So suppose A is not invertible. Well, it's almost the same thing. A is not invertible implies that AX equals to 0 has x not equal to 0 solution, but AX is equal to 0 times x if where x is eigenvector with eigenvalue and equals 0. I mean, and sometimes we proved that before, it's just that we have a different language for it now. So 0 being an eigenvalue is important. If it's not an eigenvalue, your matrix is invertible. There's other little baby theorems that are easy to prove. Another theorem. If A has eigenvalue lambda, then A squared has eigenvalue lambda squared. So check it out. The proof is simple. So if you have what? You have AX equals to lambda x for some x. If lambda is an eigenvalue, multiply both sides by A, what happens? I think you can see that this is not going to stop at 2, right? You can easily prove by induction.
Right.
Yeah. So once you know an eigenvalue for a matrix, it tells you all kinds of stuff about, associated powers of the matrix, for example. That's one thing. Now, I really should show you guys how to calculate some of these, but I'm going to resist the urge.
What?
A single
We're so
decent,
close.
a single decent eigenvector calculation takes 15 minutes.
Oh.
We got time. We got time.
We'll stay here over.
The ultimate theorem that we really want, though, is this.
Oh, we do not.
If there exists, v1, v2, vn, all eigenvectors with eigenvalues lambda 1, lambda 2, da da da, lambda n respective. And if the set beta formed by just those vectors is linearly independent, then check this out. Beta inverse A beta. I mean, all of this is eigenvectors. I'm talking about with respect to A. If I forget at any point, eigenvectors and eigenvalues always have to be done with respect to either a transformation or a matrix. Okay? Otherwise, it doesn't make sense. It's not about the space, it's about the transformation. So I should put in fine print of A. Okay. Then beta inverse A beta is simply equal to the following. Lambda 1, lambda 2, da 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 da, lambda n. In other words, let me put this in words for you. If you can find a basis, all right? If you can find a basis of eigenvectors, then if you change coordinates to that basis, your matrix similarity transforms to a diagonal matrix. In terms of the original linear transformation, that means you found a coordinate system where the action of the linear transformation is pretty much as simple as you possibly can view it. Now, if that's possible, we say that A is diagonalizable. So this is pretty much, if possible, then we say A is diagonalizable. Others. Proof.
You're right.
Oh, I'll get there. So the proof, what happens if you do A times beta? It's the concatenation proposition, all right, guys? So what you're looking at here is A, A times what? What's beta? Beta is the matrix formed by just concatenating these dudes, gluing them together as a big matrix. To multiply A like that, we just multiply A on each column. Ka-chunk, 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 ka-chunk. But what did we say about V1 through Vn? What are these? These are assumed to be eigenvectors with eigenvalues lambda 1 through lambda n. So this is lambda V1, lambda V2, da da da, lambda Vn. Right?
It's not the same lambdas though.
Oh yeah, sorry.
Lambda 1, lambda 2.
Yeah, not the same lambda. Sorry, my brain skipped. 1, 2, and now, of course, we also then need to multiply by the inverse, right? But let's see. Let's suppose the beta inverse is equal to, let's say row 1, row 2, da da da, row n. All right. So what is the thing then that you know about when you multiply beta times beta inverse times beta rather? How does it work? What is what? How can, in terms of dot products, what's throw it out there. What's W1, Wi rather, dot Vj? What does this have to be equal to? Think about beta has V, right? So V times W1 has to give you what? Has to give you 1, right? But V times V1 times W2 has to give you 0. Because when you multiply beta times beta inverse, you're supposed to get what? Right. So it follows that this is the Kronecker delta Ij. So what that means then is if I calculate beta inverse A beta here, what I'm going to get is this W1 da 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 Wn times this, lambda 1 V1 lambda n Vn. And if you calculate the dot products that are implicit in this matrix multiplication, what you've got is like lambda 1 W1 dot D1, and then you got lambda 1 W2 dot D1, and so forth, right? Eventually you have down here lambda n Vn, Wn dot Vn, right? And if you look at that, everything here is 0 except for the diagonal entries, because that's the only place where you have I is equal to j. And so if you simplify this, what you have then is lambda 1, lambda 2, lambda n. The proof of the converse, I already gave you as an example. That was our second example. I proved to you that a diagonal matrix has the standard basis as an eigenbasis with eigenvalues, the values on the diagonal, which is the converse direction of this proof, I believe. Well, I guess I didn't state it as a converse, did I? I guess that's it, but this also reverses, right? If you have, obviously if you have a diagonal matrix, we have an eigenbasis and standard basis. I guess it's a separate thing, it's not a converse, I'm gonna do it. So why care about this? Well, that is what I'm going to try to convince you of in the remaining part of the course. In part, we have two major things that are going on in what remains in this course, right? The one is this eigenvector, and we're trying to find ways to do a similarity transformation on the matrix to reveal its true nature, its underlying structure. It's one thing. The other thing we're going to pick at is geometry in Rn, like notions of distance, angle, because when you pair these two concepts together, you get some really beautiful and interesting results that you guys will like. I also think that if you can see past the theorems I'm stating today, you should notice I'm talking about a specific n by n matrix and calculating a determinant associated to it, right? So, well, this lecture may have seemed a little bit abstract to you. You should realize what's coming is much more concrete, albeit tedious. Hey, but there are websites, so, which I will share with you. Anyway, I will give you back your desk. I believe it's time, right? So, just to explain the grading, you could take Bailu. See, Bailu's like, you should give Daniel a different test just to mess with him. I'm like, hey, that's a good idea. So then I tacked on this soul-crushing awful problem at the end of Daniel's test, and then he got distracted by that and didn't do another problem. So then I felt like, to be fair to Daniel, I have to drop one of his problems earlier. But then I'm like, well, if I drop Daniel, I have to drop the worst problem of everybody's test. So then I dropped your worst problem. That's Bailey's fault. Thanks, Bailey, for improving your test slightly. Amy?